Good morning, everyone. Welcome back. In the last class, we have seen that the conditions for maximum power to be transferred over a transmission line is given by X is equal to root 3 into R. And now, in this class, we will be dealing with steady state stability. As already been said, steady state stability is the study of the system when it is subjected to small disturbances, isn't it? And during these small disturbances, the power system will be transferring or the power system will be delivering some load. And the maximum amount of load which it is delivering despite the disturbances is called as limit of the system. So, steady state stability limit often referred to as SSSL, steady state stability limit of a particular circuit of a power system. It is defined as a maximum power that can be delivered to the receiving end without loss of synchronous. This is what is referred to as steady state stability limit. Okay. So today we will try to derive an expression for steady state stability limit, and also we will see what are the nature of disturbances and how they will be impacting the power system. Before going any further, we will consider the power system whose characteristics are given by we know this equation. This is called as a swing equation. Where this is the moment of inertia and accelerating power, which is the difference of mechanical input and electrical output. Isn't it? We have already calculated, we have already done problems on this. Moment of inertia is given by GH by pi f, or you can write it as GH by 180F. And PA is basically V1, V2, sine delta by X, neglecting resistances. These are magnitudes, okay? Or it can be written as EV sine delta by X in case of a generator. This is for transmission line, this is for generator, okay? Most of the times, this is referred to as Tmax into sine delta, where this is EV by X is Tmax, and the relation between these two, T and delta, is in the form of sine curve with its peak value at Tmax. And this is called as power angle curve. This is called as power angle curve. Okay. So now we are going to derive an expression for steady state stability limit using these equations. Okay. Now, I'm going to consider the initial conditions. Let the system which I am considering is operating at an initial values of Pm, which was equal to Pe naught, and delta was delta naught. So the system was initially operating satisfactorily with mechanical power is equal to electrical power, and the initial angle, working angle or torque angle used to be delta naught. Okay. And assuming that there is a slow disturbance, assuming that there is a slow disturbance, which might have been created either by mechanical input or electrical output. So here I am considering, let it be power increment from prime mover. What does this indicate? Pm has increased. Or you can take it as reduction of load, which means Pe might have decreased. In either of these cases, my accelerating power is going to be positive, isn't it? So I'm going to consider a positive accelerating power, which is speeding up my machine. Okay. So this has resulted in change in power. Okay. This has resulted a change in power. So my power has been changed because of this. So whether there is a power increment from prime mover, my demand will be adjusted, or maybe because of the reduction of load also, my demand is thereby. So I have to adjust my mechanical power, isn't it? So because of any of these things, this results in change in torque of the machine and change in, if torque has changed, then its angle has been changed. So new value of delta is equal to delta naught plus, let us assume that the change in the torque angle is delta. Okay. So initially the operating point was this one. Okay. Now because of the disturbance, see this was the delta naught and this was the initial power. Because of the disturbance in power, maybe this point has shifted to somewhere else. This is some new value. Okay. So if the power has decreased, then the point will be here. If the power has increased, electrical power, then the point will be here. So anyway, any change in the power will be varying the value of delta. So I'm assuming that the change in the accelerating power, whether this one or this one, it might have changed the power of the machine, thereby resulting in change in delta. Okay. So now I'm trying to linearizing this point. Now I consider that P is dependent only on delta. So even though it is function of sine delta, I am just linearizing the point. So I'll take it as change in power, vertical power, is equal to dou P phi rho delta into dp. I am considering this expression by linearizing this portion of the graph. Okay. This is point number 1. Isn't it? So now in swing equation, you do have m into d square dt square by new value is delta plus d delta is equal to Pm plus, earlier I'm sticking to this one, power reduction of the load. Okay. So earlier it was Pe and now there is a change in P. So this is my new electrical part. This is my new torque angle. So I'll get it as percentage. So this was already equal to this one. So this was already equal to this one, right? So I'm neglecting these two terms because they were already equal. Okay. So this is my expression now. Okay. This is my expression which indicates the relation between the torque angle, change in torque angle, to the change in electrical power. Assuming Pm is constant, prime mover input is maintained constant. Okay. So I'm going to change this one. I'm going to solve this problem for you. Now, if you carefully see, this is minus delta P by M. So if I now what I'm considering now, this one is already right? We'll do one thing before going any further. I'll substitute this expression, one expression in two. So what I'll be getting, this is m into d square delta by dt square is equal to minus dou p by dou delta into percentage. So this is m into d square delta by d square. Okay, this is the expression for me. So I'm going to consider, let's this differential operator, whatever the differential operator is there. I'm sure of this. Okay. So I'm going to consider this as a p term. It might be some value. So mp square into d delta plus dou p by dou delta into, okay. So okay, this is some value. So this is some constant which has been calculated at delta is equal to delta now. Okay. So if I solve this one, this cannot be zero because the power has changed, isn't it? So I cannot take this one as zero. So my only other option is this one. M is a constant. This is also a constant which has been computed at delta is equal to delta naught. And dp by dt, d by dt is some parameter which I'm considering. So I can write P as percentage. This is the value of P. What is P actually? P is nothing but d by dt, isn't it? P is considered d by dt. So what is d by dt generally referred to as? It can be referred to as the rate, isn't it? Rate with respect to time. So I can write it as frequency. So this is called as natural frequency of oscillation. So whenever the system is experiencing a small disturbance, it will experience oscillations at some natural frequency. and that is computed by this particular formula. Okay, this is called a natural frequency of oscillation. Now, what will happen to this one? Now, this value, dou P by dou delta, at an angle of delta naught, this has been given negative here, isn't it? So, if this value is negative, so minus into minus, I will be getting plus square root of positive integer is going to be, I will write down here, if dou P by dou delta at delta naught is negative. If it is negative, what will happen, beta? Negative into negative, positive. Square root of positive, roots are real, isn't it? Roots will become real. If the roots do become real, then the system frequency will become a real one, and roots are real, and there will be one is positive, the other one is negative. So this will lead to increase in delta, because what is, yeah, this will lead to increase in delta, isn't it? Now, the torque angle will be increasing without bound, and the system may move into unstable state. This will happen if this value is going to be positive. On the other hand, if it is negative, yeah, if it is positive, now if it is positive, minus into plus, this is going to be minus, isn't it? So the roots will be imaginary, and there is a chance decrease in delta by providing suitable damping. The system can be stabilized. The system can be stabilized. This is the concept. This is the significance of dou P by dou delta. If dou P by dou delta is negative, the system may lead into unstable mode. If dou P by dou delta is positive, then the system can be stabilized by one or other means. Okay. Now moving ahead with this one, this particular value, which is the deciding factor of your entire thing, dou P by dou delta at delta naught, this is called a synchronizing coefficient. In the earlier unit also, you have come across this term, but that was in a different perspective. This is with respect to stability. Okay. Sometimes in some textbooks, it is also referred to as stiffness of the machine or stiffness of the power system components. They may ask you, what do you mean by stiffness of the synchronous machine? Then you can immediately say it is dou P by dou delta at the condition of delta. Okay. Now, we will just do some more conclusions now for those who are going for competitive exams for objective type. Now, what I have said, for the system to be stable, dou P by dou delta at the condition of delta naught must be positive, isn't it? So, for your side, I will do some more conclusions, which will be helpful for you. For system to be stable, Dou P by dou delta at the condition of delta naught must be positive. Isn't it? This value must be positive. Now, we will look at this one. You know that this is electrical power, which is dependent on delta. You know that P is equal to EV by X sine delta, right? So what is dou P by dou delta? EV by X cos delta, isn't it? EV by X cos delta at the condition of delta naught. So what do you mean by this one? EV by X cos delta naught must be greater than 0. This is what the condition is. You know that EV is always positive. Voltage cannot be negative. So voltage are generally treated as positive because you are considering only magnitudes, isn't it? Magnitudes are always positive. The only other possibility is for system to be stable. If I generalize this one, cos delta must be greater than 0. When can cos delta be greater than 0, guys? Cos value will be positive in quadrant number 1 and quadrant number 4. So, if I draw the curve like this, let us suppose if your P curve is like this. This is P with respect to delta, isn't it? So, where can I find positive values of this particular function? First quadrant, which means 0 to 90. Other option is fourth quadrant, minus 90 to 0. Whenever your system is operating in this mode only, if any disturbance happens, you may regain it to stability. This is the condition for this. Okay? Hope you have understood these things. This is the concept of steady state stability. And you know, maximum power steady state stability is about maximum power which can be transmitted. So if this is the expression, what is the maximum power which can be transmitted, guys? If sine delta can be made to 1. So P is equal to EV by X. That is considered to be a condition for maximum power. And this one also is termed as steady state stability limit. Triple SL is equal to EV by X if resistances are neglected. If resistances are not neglected, then automatically the maximum power can be transferred when X is equal to root 3R, which we have studied in the last class. Okay, that's it for now.